All right, this is for that ring of charge that we did in class. We can see that the point P is at some distance z away from the center of the ring. Talking about all the constants that occur in this type of problem. If we take a little pack of the charge here, the ds, that is going to contribute field at point P in that direction. If we went over to the other side, it would contribute it just off at the angle in the other direction, so that the horizontal components there would cancel out. So we're only worried about all of the components that are pointing upwards, and that would occur everywhere around this ring. And each of those packets of charge is all a distance equal to the radius away from that center point, which, if the r is the same and the distance away is the same, that means this little r is going to be the same as well. So we have all those constants, and that makes this a little bit easier. To solve for the little packet of charge, we have to integrate to find the field generated by each individual small packet of charge, and then take the cosine of that angle theta in order to figure out only the x components. We know that there's a total charge over the total length of that wire. That wire has a uniform charge density. The total length of that wire is 2 pi r. And if we took a small section of that wire with a little bit of charge on it, we would have a small section of that arc length. Looking at the triangle that is being made up of the radius, distance away, and the distance from the point, we can see that little r is equal to this, and the cosine of that angle theta is equal to z over little r, and we can substitute the square root of r squared plus z squared in for that little r. And we're going to have to substitute both of these into our starting equation up there. So that the total electric field, by summing up all the little pieces, we'll get K times the sum of dq over r squared plus z squared, and the cosine gets replaced with z over the square root of r squared plus z squared. I need to get that dq out of there. So coming back down, looking at this, dq is going to equal lambda ds. And we can combine the r squared and the z squared into that function right there. Now r, the radius of the ring is constant, the distance from the ring is constant, so z and r are constant, the lambda is constant, so the only thing that's not constant is that ds, which would be the small section of that wire, so we have to make sure we integrate over the entire length of that wire. So we're going to have lambda k z over r squared plus z squared to the 3/2. Integrate ds from 0 to 2 pi r. So that we get that should be a capital R. And if we don't know the charge density, but we know the total amount of charge, or we want it in terms of the total amount of charge, we remember that lambda is the total amount of charge all over 2 pi r. So we replace lambda with q over 2 pi r. That cancels. That cancels. K, Q, Z over R squared plus Z squared to the 3/2.